Hello everyone, my name is Kevin. Today I'm going to introduce the theorem chain rule of the advanced calculus. Here is the statement of the theorem. Let the function g from I to j such that g is differentiable at x in I, and the function is from k to L, and the domain k contain the domain I, contain the domain j. Yeah, j. Yeah. This is because if g is from I to j, then f from k to L, and the j contained in k. So the composition function h defined by f circle g is well defined. And it said that if f is differentiable at gx and g is differentiable at x, then the composition function h is f circle g will be differentiable at x. With h prime x equal to f prime gx times g prime x. Okay, and here is the outline of the proof. We define the function mu t equal to this term if t is not equal to gx, and mu t equal to the 0 if t equal to gx. The sense of this definition is that we define the mu t when t is not equal to gx by this term is because that this term is the slope of the second line, and this term is the slope of the tangent line. And when t tends to gx, the second line, the slope of the second line will tend to the slope of the tangent line. So limit mu t tends to gx equal to 0, and so we define the mu gx equal to 0 is by this sense. So by this definition, mu is continuous at t equal to gx. So the composition function mu circle g is continuous at x. This property will be used in the final step. Okay, so reformulate one. We get ft minus fg prime ft minus fgx equal to t minus gx times the f prime gx plus mu t. We obtain this relation by simply multiplying the denominator term t minus gx to the both sides of the formula 1. So if t equal to gx, then t equal to gx, then this term is equal to 0. T equal to gx, so this term is equal to 0. And the mu t equal to mu gx. And equal to 0. So this equality holds for all t in R. This equality holds for all t belong to the real number. Now we substitute t by gx plus n. Okay, the next slide. Why we can move? Sorry. Okay, I think I must clear all the notation. Okay. Okay. So reformulate the formula 1, we get ft equal to this relation. And this equation holds for all t in R. So substitute t by gx plus m, we get this relation. Because in the next step, we want to find the limit of this quotient. Since this is by definition of the df gx over dx. This is by definition the differentiable of the composite function f circle gx. So we call this relation, this equation, this relation the number of 2. So gx plus m minus gx equal to these two terms have the same circle in brown color. This term equal to this term here. So the limit of when m tends to 0, the limit of this quotient is equal to the limit of this term, and we cancel the n, cancel the coefficient n. Yeah, here is the n, and divide by n. Yeah, so we get this term. Okay, so the limit of this term is simply the f prime gx times g prime x. We have to know here that since for m is not equal to 0, here we should add the for m not equal to 0. The limit m tends to 0, vx plus m is equal to limit m tends to 0, and this term. Since vx plus m is replaced by the second slope of the second line minus the slope of the tangent line, g prime x. And by definition, this the limit of this term is 0. So this tends to 0. And since mu circle g is continuous at x, it has already appeared on the previous slide. Here, mu circle g is continuous at x. Okay. So limit m tends to 0, mu gx plus m is equal to mu of gx, and this by definition is 0. Since we define the function mu is 0 at the point gx by the previous slide in formula 1. Yeah. So this term 0, and this term is also 0. So the only exist term, so the term that we only preserve is this times this. So f prime gx times g prime x. Okay, so the above process is about the proving of the chain rule. Okay, so I think the process use some properties of the calculus, such as the continuity and the differentiability. So everyone can review this property before understanding the proof of the chain rule. Thank you, everyone.